Hi and welcome to the course on multi-agent learning. We are discussing fictitious play, and this is the second part. And in the second part we will discuss extension and approximations of fictitious play, such as smoothed fictitious play and exponential regret matching. So let's move on. Well, there are different ways to extend fictitious play or extend on the idea of fictitious play. To build forecast on counter players' behavior, not on complete history, but on recent data or on discounted data. So multiply your history with a certain discount factor so that history becomes less and less important. On perturbed data, so data with errors or noise, or random samples of historical data. To give not necessarily best responses, but absolute greedy responses, or perturbed throughout, that is, give best responses but sometimes with an error, or give responses proportional to expected payoff and then random. In order to understand, we'll follow closely Peyton Young's chapter on fictitious play, in which he, on its turn, follows closely Jordan's framework for fictitious play. And it's called Framework for Predictive Learning. So forecasting rule for a certain player is a function that maps a history to a probability distribution over the opponent's actions in the next round. So here, this is a set of all histories, and this is a set of all counter action profiles, and you can have a probability distribution over the set of all counteraction profiles. And then a response rule for a certain player is a function that maps a history to a probability distribution over that player's own action in the next round. So, like so. Then a predictive learning rule for a certain player is the combination of a forecasting and a response rule. And this framework, according to Peyton Young, can be attributed to Jordan. And the forecasting and response rules are deterministic up to the probability here, because both have a probability component. But the algorithms themselves are fixed. This means that reinforcement and regret do not fit, because they're not involved with prediction, they are only involved with past payoffs. They're not interested in predicting the behavior of the opponent. Now, how does fictitious play fit in this framework? Well, if you have a history of play up to and including round t, and then phi sub gt is the empirical distributions of j's actions up to and including round t, so g is another player, then the fictitious play for forecasting rule is given by the product of, well, this is the product symbol, the product of all empirical distributions of other players, So because you form a product distribution out of individual empirical distributions, you are assuming in fictitious play that your opponents act independently, that they're not coordinating against you or for or in favor of you. Now, we have a fictitious play forecasting rule, and if G plays best responses with respect to this forecast, then we have fictitious play. So as I already explained, every player attributes a mixed strategy to player G, and this mixed strategy is formed out of the observations with respect to player G. And this product distribution reflects that the mixed strategies are assumed to be independent, so your opponents are not coordinating their behavior. So these are the simplifications in fictitious play. Now, one variation of fictitious play is smoothed fictitious play. We need some notation. P sub minus I is the strategy profile of the opponents as predicted by the forecasting rule in round T. So we're not using the index T here apparently, so the round T is left implicit. U sub I, X sub I, P sub minus I is the expected utility of a certain action of player I given the strategy profile of his opponent. And well, the predicted strategy profile, and this is the actual strategy profile of all players, and in particular for player I in the next round. Now the task for a forecasting algorithm and giving a response rule is to define the strategy profile of players in the next round and the predicted strategy profiles of the opponents. Now the idea for smoothed fictitious play is to respond randomly but proportional to the expected payoff. Now you can, well, the order is a bit strange here. You can the probability that you play a certain action given the strategy profile of your opponents as predicted by the forecast function is given by the utility that you obtain given the strategy profile as predicted by your forecast function normalized by the other utilities. And well, you may define this as a strategy. Well, that is strictly proportional, and the alternative is of course to play with the proportion through softmax function, or the control response rule as it is called, or mixed logic as it is called. So let's consider the softmax function. Softmax respects best replies but leaves room for experimentation. So you have a tuning parameter that's called the temperature, and if the temperature is high, then every action is considered equal in value. But if you decrease the temperature, then the best responses get a higher share of being chosen. Get a higher share on the disk, and the probability of being chosen is higher. Now there is a theorem which you won't prove because it's outside the scope of the lecture. So Fudenberg and Levine. If you have a finite game and some given accuracy, which can be very small, as small as you like. So if someone gives you a certain accuracy, so let's say 1,000, and then if a given player uses smoothed fictitious play with a sufficiently small smoothing parameter gamma, which of course depends on the epsilon, then his regrets are bounded above by this epsilon, this accuracy, almost surely, so with probability 1. Now Young does not quote a proof of Fudenberg and Levine, but shows that in this case epsilon regret can be derived from later and more general result of Martin and Mascolel, but we won't go into that. And it follows from Blackwell's approachability theorem, which we won't discuss in this lecture because it's beyond our scope. What I can say about it is that it generalizes max-min reasoning, so about maximizing your minimal payoff. but then to vector valued payoffs. So, hey, this is interesting. Fictitious play is connected to regret. So here we see a first connection. And there's another interesting connection with no regret, because if all players follow regret matching, then we already know that they converge to a coarse correlated equilibrium. And we already discussed this, but here's the definition again for a coarse correlated equilibrium. Distribution, probability distribution among all action profiles may or may not be the result of the product of strategies. Then this probability, this joint probability distribution is a coarse correlated equilibrium, or Hanan said, if no one wants to opt out prior to a realization of Q in the form of an action profile. So if everybody knows Q, but not yet his own action, so only with this knowledge of this joint distribution, then no one wants to opt out. And then a coarse correlated epsilon equilibrium is if no one player wants to opt out to gain more in expected utility than epsilon. It seems to be an insipid variation to coarse correlated equilibrium, but epsilon Nash equilibria and absolute coarse correlated equilibria are important concepts because these are attainable by computation. And for example, epsilon Nash equilibria are obtainable by learning, but Nash equilibria themselves are very difficult to obtain, and if not impossible. Still ongoing research. But for epsilon Nash equilibria, it's possible because you can divide up the strategy space to carve it up in small sections, and then it's attainable. However small epsilon is, because then the resolution is simply higher with small epsilon. So then there is, given the knowledge of a coarse correlated equilibrium and a coarse correlated epsilon equilibrium, there is a theorem of Fudenberg and Levine that says if you have a finite game and a certain level of accuracy epsilon, then if all players use a smoothed fictitious play with sufficiently small smoothing parameters gamma sub I, so every one player has a own smoothing parameters, then empirical play converges to the set of coarse correlated epsilon equilibria with probability 1. So the first theorem essentially says that smooth fictitious play limits regret, and smooth fictitious play converges to epsilon coarse correlated equilibria. So both are connected to regret in some sense. Still, this is not the best we can do, because there is another learning algorithm with no regret and convergence to true coarse correlated equilibrium. And we will discuss that now. It's called exponentiated regret matching. Exponentiated regret matching. So if we have an action J, and then so we're rehearsing some terminology here, some notation, and then U bar sub I sub t is player I's realized average payoff up to including round t, and phi sub minus it is the realized joint empirical distributions of I's opponents. And then mu bar sub I g phi sub minus it is player I's hypothetical mean payoff for playing action J against this joint empirical distribution of I's opponents. And then as usual, R bar sub it is player I's regret vector in round t. And then exponentiated regret matching, which is discussed in Peyton-Young's monograph on page 59, is defined as having probabilities in the next round that are proportional to positive regrets, but not only to positive regrets, but to positive regrets to a certain constant exponent, where this constant exponent is larger than 0. Of course, for this exponent is 1, we have ordinary regret matching. And then a theorem on exponentiated regret matching ensures that the individual players have no regret with probability 1, and the empirical distributions of play converges to the set of coarse correlated equilibria. Now, to compare fictitious play with smoothed fictitious play and exponentiated regret matching, first, Peyton-Young makes a distinction between best reply and better reply strategies. He argues that fictitious play is a best reply strategy because it plays a best reply. Well, no need to stutter here. A best reply to sampled past play, and because it always plays a best reply. And regret matching may be called a better reply strategy because it plays a reply for which the expected payoff is better than past average payoff. Now, smoothed fictitious play is neither one of the two. It's not the best reply strategy because it puts positive probabilities on suboptimal actions, or it may do so, and it's not a better reply strategy because it's not concerned with past payoffs. So fictitious play plays best responses, does depend on past play of the opponents, obviously, puts 0 probability on suboptimal responses, and smooth fictitious play plays with softmax, has a positive probability of playing suboptimal responses proportional to their estimated payoffs, and indeed does depend on past play as fictitious play on opponents, and puts probabilities on suboptimal responses. Now, Peyton-Young argues that a smoothed fictitious play has the property that it approaches fictitious play in the limit when the probability to play suboptimal actions approaches to 0, which is quite an intuitive result. Now, exponentiated regret matching plays regret suboptimally, that is, proportional to the power of positive regret. Does depend on its own payoffs. Also, as a smoothed fictitious play, puts non-zero probabilities on suboptimal responses, and interestingly enough, it approaches fictitious play when the exponent becomes larger and larger. So, to say it once again, but then in the form of a table, to tabular the results. Fictitious play and smoothed fictitious play depends on past play of opponents, but exponentiated regret matching does not. Exponentiated regret matching depends on known past payoffs. Fictitious play is a best reply algorithm. And smoothed fictitious play is when gamma approaches 0, and exponentiated regret matching is when a goes to infinite, because it then also approaches fictitious play. With fictitious play, we do not speak of individual no regret, but with smoothed fictitious play, we do speak of individual no regret. And smoothed fictitious play, as well as exponentiated regret matching, has relations with coarse correlated equilibria. Now, to conclude, I want to show you a comparison between fictitious play and Q-learning and replicator dynamic. I should have included regret matching as well, but that's something for the future. So let's open. So here we have an arbitrary game between two players and 5 actions per player each, with 1 equilibrium. This is not an arbitrary game, but in this case it's a rock paper scissors game, but then with 5 actions instead of 3, and then there's 1 equilibrium which is uniformly distributed among all actions. The red square denotes where Q-learning is heading. The green square denotes where replicated dynamic is heading, which we are about to discuss, but it's also a learning algorithm. The blue square is where fictitious play is heading. The squares may overlap, which is likely in the case of Nash equilibria. And then, well, for example, if you have a yellow square, it means that the results of Q-learning and the replicated dynamic overlap. So you see that, for example, in the 5-action rock paper scissors game, obviously fictitious play and Q-learning and replicated dynamic do not converge, because the rock paper scissors game is a typical nasty game where all positions, all action profiles, other players are tempted to move away from that action profile. So that's a particularly bad example. So let's do a random game with only mixed equilibria. Well, not just a random game. With 5 actions. We have 3 pure equilibria here. So this is just a generally a randomly generated game with 3 Nash equilibria here, pure equilibria, and 2 mixed equilibria. So if we walk through the equilibria, we can do so. This is the first equilibrium. This is the second mixed equilibrium, which is mixed. This is the third equilibrium, which is pure. This is the fourth equilibrium, which is mixed, and this is the 5th equilibrium, which is pure. So these are the equilibria. So we may hope or expect, with our knowledge of fictitious play, that fictitious play does not always converge to a Nash equilibrium, but under some conditions, which are listed in the chapter 7 of Shoham and Leighton Brown. For example, for potential games, or for zero-sum games, or for n/2 games, fictitious play converges. Well, if we let it run, let's see well, the various learning algorithms. So we see that the replicated dynamic, which is green, converges to the first Nash equilibrium, pure equilibrium. Fictitious play, which is blue, converges to the second pure equilibrium. And Q-learning converges to, apparently converges, well, slowly converges to the third pure equilibrium, but takes a long time to correct itself. So it would be a nicer demo if we also have no regret learning here. And depends, of course, on the initial conditions to where the different learning algorithms converge. So Q-learning hovers here in frequency between action 2 and 3, the first player. Let's repeat this experiment with a couple of other random games. Again, Q-learning misses out on pure equilibrium, but there are mixed equilibria, so let's see if there are. So let's remember the position of Q-learning here, and let's see if it lands on one of parts of the mixed equilibria, which is not the case. You see, the mixed equilibria have nothing to do with this square. And replicated dynamic converges apparently to some suboptimal. No, this is not even a Pareto optimum, because these two are here. So most of the NetLogo apps are downloadable from the site. Only the app I just show you, which is here now. Well, Q-learning, replicated dynamic and fictitious play. So this is it has a bug which this afternoon I tried to fix, but I didn't succeed. But if the date is later than May 13, you see a date is later than May 13, then there is a probability that the bug is fixed. Okay, thanks for watching, and hope to see you on the other side. Bye.